today is the happy day when we have reached what I feel is the most interesting part of the course, which is more graded geometry, like super geometry in the first instance. So forget everything you learned so far. I mean, not really, a bit.
Okay, so by the way, is it visible on your video? It's a little bit shiny on the board.
Yeah, it's invisible, but it's a reflection. But if I, yeah, I think it's probably okay. Yeah, it feels okay. Yeah.
Okay.
Thanks. Okay, so this is a thing which is generally interesting and useful to know by itself. It's surprisingly efficient in many ways, especially the things that I keep encountering. And so later on we will connect this with Courant algebra. They will kind of embed as a special kind of structure in this. But this is a very general thing, so let's spend some time on working with that. And the way I prepared this is that since this is a mathematical course mostly, so I will try to be more rigorous, maybe today. I will try to be completely rigorous, and then we will try to develop some intuition on like what is happening, and then later on we will kind of work more casually once we have the intuition, and then we will stop writing all the details. But like for today, I want to be kind of completely rigorous, so hopefully people won't get bored. I think it's pretty exciting anyway, at least to myself. But I will mark it as a star subchapter, which means that I won't. For those of you who are taking the exam, and then this won't be on the exam. The thing coming after that, which is kind of more casual, that one will be. So I will the star. So star means that that's kind of like slightly more advanced. So let me start by talking about sheafs. So many people are scared of sheafs, and they shouldn't because it's a very beautiful object. So the idea is that this is a useful type of structure when you work with local data. So it's all about local data. And okay, so let's start the definition. So the first step towards defining a sheaf is to define a pre-sheaf. And we will say that a pre-sheaf for now, pre-sheafs of sets. I will denote it by curly f. This is kind of standard to denote them by f, which comes from the French name for sheafs, which is faisceau, where the thing originated. And in general, people use lots of agricultural terminology with sheafs. So there is stalks, stacks, gerbs. Okay, so this is given by the following data. I will be first explicit and then I will tell you a more concise definition. And of course I forgot, so this is a sheaf F on some topological space. Okay, so forget about manifolds for now. It will be more general. Say we have a topological space X and we want to define what a pre-sheaf is. And so a pre-sheaf consists of two sets of data. So first of all, for every open set, U in X, we have a set F of U. So we have an assignment to every open subset of the topological space. There is some chosen set. And we have a bunch of maps. So for every, if we have two open sets, this induces a map between the corresponding Fs. We have a map from the bigger one to the smaller one. No, okay. From the bigger one to the smaller one. And the way you denote that is that if you take f of v here, and take some v, then the image of that you will call v restricted to u. This is the standard. You use the restriction notation. And the conditions of this, there's two conditions. First one says that for the inclusion of the set into itself, the map is the identity. And the composition is respected. So if we have three open sets, so say U inside V inside W, then the obvious thing. So if you take take the thing in the biggest thing and restrict it gradually, further restrict it to V, and then the result you restrict further to U, and this should be the same as directly restricting to U. Okay, so restricting it like this and like this is the same as restricting it all the way. Okay, and the more concise way to say what is happening is that, in other words, a pre-sheaf is a functor from the category of open sets taken as an opposite category into sets where this guy this is a category where objects are open sets. And there's one morphism, and there is a morphism between U and V if and only if U is inside V. And this op just means that I'm reversing the direction of the arrows. Okay, so if you know what functors are and categories, then you can just say that this is the thing. So it's a contravariant factor. It's a contravariant functor of the category of open sets. From that to sets. But expanded means this. And so this is the fact that functors preserve identities, and this is the fact that functors preserve composition.
And the morphism is from U to V, or like that's your connection?
Yeah, I think so. Yeah.
It's like the inclusion method.
Yes.
I mean, otherwise you would take the opposite, so I mean both would work, but...
Right. Yeah, I wanted to make it, the standard. So it's like the category open set is a partially ordered set. I mean, sorry, the open sets on a space is a partially ordered set, and if you have a partially ordered set, then you have a category of this construction where you have an arrow if and only if one is bigger than the other. Thanks. Okay, then one thing you can do is you can replace this more. Okay, so this is this was sets. So okay, so can do more general stuff. So you can replace sets can replace sets by groups, rings, etc. Yeah, algebras. But yes. Okay, so yeah, let me see. Algebra, thank you. And the thing that changes, of course, is this thing would change. The name, I mean. The fact that the assignment produces a set would change, group, ring, etc. And whenever you say a map, then you mean the morphism in the corresponding category. So homomorphism of groups, homomorphism of algebras, rings, etc. Okay, so that was the most boring definition. So now examples of that. How does it fit into our geometry? So example, couple of examples. So if, let's say we take directly M to be a manifold, then the following things are sheafs. So you can take F to be smooth functions, for instance. Okay, what does this mean? It means that, so the assignment is that to every open set, we assign the algebra of open functions, or set, or whatever, depends on what you want your sheaf to be. Okay, so the assignment just tells you that if you have your space, and to each open set you have a some assignment. In this case, an assignment of smooth functions on the open set. And this obviously, because this thing is constructed pointwise, I mean functions are defined pointwise, then that it's kind of obvious that if you have like, you know, that there is a restriction map, and the restriction map satisfies this composition that if you have a function restricted to smaller and yet smaller thing, is the same as if you would restrict it directly to the smaller thing. So all the types of structures that you, well, lots of types of structures that you know do have this property. So, okay, I will write a bunch of things, and then we will see later on when we define sheafs that not all of these are actually sheafs, but they are all sheafs. So, in preparation for that, write a bunch of other stuff. So, one thing that is definitely a sheaf is constant functions. Okay, again, it's just the same thing. Give me an open set, and I give you constant functions in the open set. Slightly differently, you can do locally constant functions. Why is this different? Why are local functions different from constant functions?
Because it's a sheaf.
Thank you. So if I would have an open set which would be not connected, then in the first instance the corresponding pre-sheaf could have, like, in this case I would need to have the same value here and here, while here it can be one value here and different value here. Okay. Yeah, just locally constant is different than constant. Then you can have p-forms. You can have closed p-forms. You can have exact p-forms. You can have vector fields, various tensor fields. You can have sections of some vector bundle. Okay, all of these are examples of pre-sheafs. And in all of these cases actually they are pre-sheafs of algebras. No, that's not true. Yes, that's true. No?
Sections, forms.
Ah, okay, well. Okay, yeah. Okay. Apart from the first three. This would be okay. Okay, yeah, right. But vector spaces, let's say, all of them are sheafs of vector spaces. Now, okay, now what is a sheaf? So sheaf on a topological space X is a pre-sheaf. So it's the same type of data, pre-sheaf, but it has one more condition or two, depending on how you see it. Satisfying the following extra condition. That for all open subsets U of X, and all open covers of those of U, and here by open cover I mean that such that all of them actually are inside U. Okay, I don't want them to overlap. So I want really like I would have three open. I would have something like this, and this would be my U1. This is U2. This is U3, and the total thing is U. Okay. This is what I mean. I mean, all these things in the cover should be. This is U. So I don't want pictures like this. That this is U, and then you have an open cover which looks like this. That's not good. For all open covers of every open subset, as absolute subset, if I have a bunch of if I have a bunch of sections of oh yeah, I didn't say it, or did I say? No, I didn't. So this set F of U, this is called elements of this are called sections of the sheaf. Okay, that's why, for instance, sections of a vector control were a sheaf. I mean, that kind of shows you the nomenclature. Okay, so now the condition says that if I specify a section over each of these guys, alpha, and I have and they coincide and overlaps, so such that for all alpha beta, if I take f alpha and f beta, this guy lives in u alpha, this guy lives in u beta, but I restrict them to the intersection u alpha intersection u beta. So if I have a bunch of sections such that they coincide on intersections, then there exists a unique section on the whole thing. F section over U, such that the individual guys are simply restrictions. Okay, so in terms of pictures, so if I have a condition is that I can glue things together and I can glue them uniquely. So if I have some section defined over this guy, and I have a section defined over this guy, and I know that if I restrict them to the middle, then they are the same, then I know that there should be precisely one thing that lives on the whole thing, which restricts to one and to the other on the respective open sets. Okay. Okay. Now exercise to put it all together. What are now, given looking at these things, which ones do satisfy the sheaf conditions and which ones do not? Which ones do not? Each person can only say one, so we give more.
So exact not.
Okay, maybe let's go to that later. So, smooth functions, are they a sheaf? Do they satisfy the gluing condition? If I have two smooth functions defined on that picture here, and they coincide in the middle, are they smooth? Do they correspond to a smooth function on the whole thing? Yes. So, so how should I mark this? So, let's say examples will be using the green color. So, this one is a sheaf. Now, is this thing a sheaf?
No.
Why not?
So if you have two non-overlapping opens,
It's bigger.
this and that, then you can choose like a section with different values on each open. So this is a section, but it doesn't extend to a section with both.
Very good. So if I take a picture like this, I have two opens that don't overlap, and I take a function here, which is constant, let's say it has value 1, and I take a section here, which is value 2. Okay, so I have precisely this, I pick these f's, and I know that on the overlap they coincide because there is no overlap, so there is no condition. So this is a good, this satisfies the first half of the sentence, but the condition is that there should exist a section over the whole thing. So there should exist a section on this open set, taking all together, which is constant, and which restricts to these two, and it doesn't exist. Okay, because the section constant on both of them would have the same value on both of them. Okay, so this is not an example. You cannot glue things nicely, so this is red. Non-examples. But by the same token, you can see that the locally constant sections are a sheaf. Okay? Because this example, for instance, this example that I mentioned, it works. So this is a locally constant section over this first guy, this is a locally constant section over the second guy. Does there exist a locally constant section over the union which restricts to these two? Yes. Because function which has value 1 here, function which is value 1 here and value 2 here is a locally constant function. Okay, is that clear? Okay. Now what about p-forms? Yes, thank you. What about closed p-forms? Also, because if it's closed, if I have two closed forms which all coincide on the overlap, then closure is a local condition. So taking extending the whole form. If I have closed from here, I take the union of that, so I consider it as a closed form on the whole thing. It will still be closed because it's a local. Now what about exact forms? Okay, and now what is why are exact forms not? What would be the counterexample?
Then we close one that's not exact.
Sorry? Yeah, but okay, but in terms of the picture.
Okay. Locally every closed form is.
Right, but I mean, what would I take the open sets to be? So
You can take a circle and cover it by two sets, and then have.
yeah, thank you. Circle is better than what I had in mind. Okay, yeah. So we take circle, and I would take two open sets. One would be this, and the other one would be this. Okay, they're open. Yeah, and I can take the function. I can take the one form d phi, define on one of them, and define on the other one. Okay, phi being the angular coordinate. So this is a one form. You know that this thing this thing is a well-defined form on the circle, but it's not exact, even though it has a d in it, because this function is not globally defined. Okay, so this thing is an example of a closed form, which is not exact, as was said here. But okay, so how does it fit in the example? So if I take this open set here, it is contractible. So this guy, okay, sorry. Once again, I take these open sets, and I take d phi defined here. I take d phi defined here. They coincide and overlaps because it's d phi. It extends to a form on the whole thing, namely d phi, but it's no longer exact. Even though it was exact here and exact here, if I glue them, it will no longer be exact. So d phi is exact on here and also on the other guy, but not on the circle. Okay, so that's not a sheaf. In kind of probably the way you can imagine that is because I said that sheaves are useful for keeping track of local data. Is that exactness is not kind of it's not really a local property. It's like like every closed form is locally exact. That's true, but like if you want like just to see whether a form is exact, it's not enough to just look at the neighborhood of a point. You need to examine the global properties, such as in this case the topology of the circle. So that's why you see that this kind of clashes with that philosophy that sheaves are supposed to be local in that sense. And what about sections of a vector bundle? Yes, that's the same as functions or forms. It's just something that's defined point-wise. So yeah, it works.
Can I have a question?
Yes, please.
So far all the examples that failed to be a sheaf, they failed because there was no section, global section.
Oh dear. Okay. Yeah.
Yeah. So do you have an example where the other thing fails, where the thing they grew to is not unique?
Okay. Let me think. If anyone, this is a question for the audience. What is an example where the other condition fails? So these things here, they had the property that they were defined point by point. And in this case, constructing the thing, if you had an overlap of things and you wanted to construct the whole thing, you just added them point by point. That's why they all extended in a unique way. So in searching for something that does not satisfy the uniqueness, you should go beyond this. So you should think about stuff that's not defined point by point, but could be like okay, I would have to think. It's a good question. Let's leave that as an exercise. Okay, that might be okay after the race.
potential is defined up to a closed thing. So it is, they glue, right, because there is a potential that glues everywhere, but it's ambiguous. Because you can choose many different potentials. But I don't know.
Yeah, so
So
yeah.
ChatGPT has an example which is locally constant functions, modulo constant functions. So kind of quotient thing, you know. So that
Okay.
if you try to do this, then you can choose different constants and different sets, and they then I don't know if it's true, but it looks like.
Okay.
You need some kind of gate symmetry, it seems, kind of this type of thing.
Okay, 2 points, discrete topology. The value over each point is a non-trivial set, but the value over both points is a trivial set. Wait, no. No, the value over both. The value over each point is a trivial set. The value over the whole thing is like a full-element set. Then the restrictions to both sets always agree. That always satisfy the shift condition. But you have multiple ways to lead.
Let's write it down. That sounds fun. So that's the same thing as saying that the sheaf is the identity map from the space to, well, I mean the value of the sheaf is literally the same as the, which that you said, it's the same as the set.
Yes.
So, okay, so, example, let's see. So you have 2 points. And now we define a pre-sheaf. It says that pre-sheaf is a map from the open sets. So I need to say what it gives me on this, on the left point, on the right point, on both points. Because these are the 4 open sets. And the organic suggesting is that the state is to be points, and here are 2 points. So those 2 things are mapped to singleton. This is a user union of 2 singletons. And is this a pre-sheaf?
Yes, because they're like terminal objects.
Wait, what is the restriction? What is the map from here to? Oh yeah,
There's
There's
only
only
one
one restriction. Yeah.
Yeah.
All the sheaf maps are kind of
Yeah.
given. There are no choice.
Like one point set is
Oh yeah, right. Because you go from bottom
Yeah,
to
yeah.
up. Yeah, so the sheaf map should go from the bigger set to the smaller. So in this picture they should go above, but there is always a unique map to 1 point or to an empty set.
No,
No,
I
there's
think
no
that
map to the set.
the value of the on the empty should
It
also
should
be
be also 1 point.
Oh yeah, sorry. Yeah. Oh yeah. No, I forgot to mention. Okay, yeah, that was my funny example that I had. Okay, later. Now it's actually coming. Okay, yeah. Yeah. So we will comment on why this is in a moment. Right. So you take this one. It's a pre-sheaf as we just checked because there is no ambiguity. There is only one map. Now is this a sheaf? So if you take an element in here, an element in here, which means, well, that's the point. On the intersection, there's 3 intersections, so there's no condition. So there should be exactly, by that condition, there should be exactly, if it were a sheaf, there should be precisely one section of the whole thing. So one thing in here, that restricts to both of them, but actually both of the points restrict to both of them. So this, yeah, so the identification, the uniqueness fails. Beautiful. Good. Okay, good. Now, oh yeah, one more note I want to say. Which there is many operations with sheaves. Sheaves are, I mean, the theory of sheaves is a beautiful subject. It has high value in like algebraic geometry and many other things, in differential geometry. And you can do many things with sheaves. Sheaves are good because they, in some sense, because they form an abelian category, which is a great object to work with, and they have many beautiful properties. There's many constructions, but we won't need essentially any of them for what I want to say. But just mention one thing. So note, technically we don't need this. So if you have a subspace, okay, so is a subspace of a topological space, then we can define an induced sheaf, and f is a sheaf on the big guy. Then we have an induced sheaf induced sheaf, which is not f induced, f reduced to restricted to y on y. Simply by, like if this was x and this was y, a sheaf should be something that assigns to an open subset some data. But open subsets of y, in particular, are open subsets of x. Wait, is that true? Yes, that's true. Right, that's how topological subspaces work. Okay.
Y needs to be open in X, right? This will.
Yeah, the premise of an open should be open.
Yeah.
The premise
Yeah.
of an open is an intersection of y.
Thank you.
Not if Y is a closed subspace, then Y is an open subspace in Y, but it's closed in X.
Wait. Wait. Sorry. So you're saying that we need an openness here?
I think so.
I mean, it's true that if I take like a closed subset of like exact forms. Let's see. So,
especially you need the F restricted to Y to value something on Y, right?
yes.
And you want that to be F of Y, right?
Yes.
And for that to make sense, Y needs to be open.
Yes. I agree with that. Yes. But is the openness enough to?
I think so.
So if you have an open,
If you have an open subset of an open subset in the subspace topology, then it's open in the
okay. Okay. Because
subset topology, an open subset of the subset topology is when you have when it's the set is a restriction of an open subset,
Right.
the big one, and the subset.
what is the big one in this case?
The big one is X. Right, so open subsets in Y are exact intersections of an open subset in X and Y.
Yes.
Right. So if Y is open, it's an intersection of two open subsets. So it can
Oh.
in X.
But then wait. But then this is
Do you know what the restriction to Y is if Y is not open? You wouldn't know, right, from the definition of the sheaf.
yeah. Even that would not be clear. Yeah. But
No, because for sheaf you have restriction to opens.
for sheaves
I
only
would-
work in open sets.
I would
No,
not
no.
evaluate F of
You
F restrict to Y
unless you do some kind of like stock construction,
Yeah.
right? Like recording over all plus
And
containing
then,
y.
yes.
But this requires more assumptions,
Right.
Right.
which are obviously this method.
Keep it open. Forcing away something inconvenient.
Okay, okay, yeah, so like what
Yeah.
Ruda was saying. Okay, so if it's like this, then it's fine, and because this small guy is open in the whole thing. Right. Okay, thank you. Sorry for the confusion. Okay, good. Now okay, so one note is that if read correctly, then if you have a sheaf, then the evaluation of the sheaf on an empty set should be a point, or more generally a final object in the category of your in which the sheaf is valued. So for sets, this would be this. And the way to see this, well, it's good to remember it because to derive it is kind of, but in principle it follows. So this should follow by taking empty covers of the empty set. The empty cover of the empty set. Okay, so this is for the, as people say, for the lovers of the empty set. Like technically it follows from these axioms that, you know, like, because the axiom says that if I have this open cover U alpha U, and if I have a bunch of F alphas, which this is a quick recap, if bunch of F alphas which coincide and overlaps, then there exists a unique F which restricts to them, which is a section of the whole thing. Sorry, I wanted to distinctly not use curly letters. Okay, so if you have an empty set, which is a subset of a topological space, you can cover it with an empty cover. So namely that this is an empty cover. And then whenever I have a bunch of F alphas defined on all of them, which I always have, I mean, so this bunch would consist of a, okay, what does it mean to have a bunch of F alphas? It means that I have an element in product. Should I take it to be product of F alphas? Okay, so I take a product of these sets and I choose an element in there. That's what it means to kind of have a bunch of F alphas. Now, if this index set was empty, if I had an empty cover, then this was an empty product, which is the same as a point. So, like a trivial, like a singleton, right? So, am I messing this up? Hopefully not. So, the point is that I can choose this bunch of F alphas, namely to be that point. Then there should exist a unique section which restricts to them, which means that there is precisely one point on the whole thing, namely on the empty set, or something like this. You can. It's not terribly important, but you know, why not mention this?
But it doesn't have stars, so we will ask about it in exam.
No, the whole section of the star.
The whole section.
Yeah. I'm consistent. Okay, so now the big question is that now why do we need this? We need this. And so the philosophy here is that, and this is a philosophy underlying a lot of, well, the whole supergeometry, gradient geometry, algebraic geometry in some sense. So the idea is that if you work with spaces, so let's say manifolds, let's take the manifolds for a moment. So if I have a manifold is a nice kind of object. I can draw a picture. It's like a set with some extra structure. But oftentimes when I work with it, then instead of talking about points, you talk about functions, vector fields, and forms, and tensor fields, and whatever. So, for instance, functions. So let's say we have this interesting object, which are functions on the space. This is an algebra. Okay, so this is a commutative associative unit geometry, even has a unit algebra over real numbers in this case. Okay, and the idea is that in these kind of approaches, I forgot to mention non-commutative geometry. That's what we're field where people use this. So instead of talking about this, you choose to talk about these guys. Because anyway, if you remember like things like Cartan formulas and everything, it's kind of all happening in here and you are not referring to the points, but instead of some algebra to some algebraic operations in here. So, and it is very common in many instances that we have actually something here that is non-commutative. Okay, so sometimes we have a more general object, let's say a non-commutative algebra. But for some reason, we still want to talk about it as if it was algebras of functions in some space. So, as I said, but still, I want to pretend, I will comment on that in a second, that it is C infinity of some curly m, this is how I write curly m, or some space in quotation mark m. And of course, that space is not really a space. It doesn't correspond to like a topological space or like a set in this sense because function would then be commutative. But sometimes it's convenient to do that. And in particular, because then we can use various stuff that you can do some thinking. That's one example of why we want to do that. But then we can use things like differential geometry or like notions on differential geometry. We can think of in terms of pictures. Okay, let's say and draw pictures. That's important for some people, for myself. Okay, so that's kind of the idea. We will instead examine more general classes of algebra, but we will still can pretend that they are functions on some abstract whatever. And so let's go with A, algebra A. Algebra A. And so what the thing that we will do to make this kind of more formal, let's say idea one, is that we take A to correspond to a sheaf, to be a sheaf over some space, maybe manifold, over some manifold. Let's say, okay, let's use n, maybe, not confused with the above. So, okay, so so in some sense I will do some sort of hybrid construction. But I will study the general algebras and I will want them to be partly corresponding to some real space, but to have some extra stuff. So I want in particular that I will want that functions of that manifold are a part of A, but there can be more. Okay, so I kind of choose, yeah. I go kind of halfway. I study these algebras, I pretend that they correspond to some space, they do not really, but there is a sub part of them which actually does and which can have interesting and non-trivial topology. And so then the idea too is that I reformulate as much as possible of the ordinary geometry in terms of some algebraic operations which will carry over directly here. So reformulate as much as possible of differential geometry in a suitable algebraic way so that we can then carry it over so that it easily generalizes to arbitrary A's. For instance, we know that vector fields you can think of as being derivations of algebra of functions. And if you say it like this, then this works for any algebra. It doesn't have to be algebra of functions in a manifold. So vector fields are an example of thing that easily generalizes. Yeah, this is in fact an example. Vector fields, which originally were taught to think of them as arrows on some space. But you can equivalently say that they are just derivations of the algebra of smooth functions. And so if I now take this and replace it by general algebra, then I can still pretend that these are vector fields. And I can draw pictures sometimes, even though they don't really correspond to anything realistic, but I still do that. Other things that you can do, you can, instead of talking about coordinates, let's say x mu. So what were coordinates? If you had a manifold, there was some open subset that mapped to like some Rn, and then pulling back these coordinate functions, you get coordinates in the manifolds. But if you think about them abstractly, then what do coordinates do? They kind of allow you to build functions by multiplying them, possibly with some completions. So this, I can just, instead of coordinates, I can talk about generators of the algebra of smooth functions, right? Because maybe squinting my eyes, any smooth function is a polynomial in coordinates. I mean, not really like complete, but okay. This is the ideological part. So similarly, subspaces or submanifolds. Again, there's a concrete picture to have in mind. There's subspace. So what they correspond to is ideals in the algebra of functions, namely the ideal functions which vanish on that submanifold. Okay, so if n is in M, then you can take the ideal to be functions such that if you restrict them to n, then they are zero. This is called the vanishing ideal. So many of the objects have some nice algebraic counterpart descriptions. And maybe one last thing, a smooth map n to n, which in this picture was, you have these two blobs, two potatoes, and you have a map that to every point here you assign a point in here. You know that if you have such a thing, then on functions, if you want to talk about functions, you can pull back functions. So this thing induces a map, an algebra map on the functions. This is a morphism of algebras. Okay, so this is kind of the general strategy. You need, for some reason, to talk about symplectic forms on a supermanifold. So what you do is that you kind of figure first what those things are. So you figure first what those things are algebraically, like how you can write them using the algebra of functions without ever referring to points and boring things like that. And then you just proclaim that to be your definition in the general case. although it sounds maybe silly, it's a beautiful and very powerful idea. So much for the kind of ideas. Now let's be more concrete and let's talk about the particular brand of this subject, which is called supermanifolds. So any questions in while here? Any more questions?
I'm going to explain if you have a morphism, if you have a smooth map, what should we give on the level of sheafs?
Sorry, second?
So we need to explain if you have a smooth map end to end, what should we give on the level of sheafs?
We will do that in a special case of supermanifolds only. It will be the more, because if you have like various things you can do with sheaves, you can have like okay, we will see in the special case of supermanifolds.
And then, so if you have a map of topological spaces, you have a push forward factor between the sheaf categories, which is not very easy to define. And then you can do something like a restriction, which should be a left edge join, and you can compute it, but it involves doing some kind of like small key construction. You take going it over all opens which contain the image of your open or something like that. So in what you wanted in the example, it's good that you want you only take an equivalent of open.
Okay.
You can define full bag of a sheaf for a general map of topological spaces, but it requires a bit more technology. But there is a formula.
I see.
It is a sheafification of some of the left join of the push.
Thank you. I see. Yeah. So so the theory of sheaf is a beautiful subject, but here we are touching only we are not talking about. I mean, I won't probably mention things like sheafification and things like this, but they are kind of exciting things to look at. Yeah, this is only like a skim through some ideas that are necessary for what I wanted to say. Okay, so let's now talk about supermanifolds. And I will put a star here as well because this I will kind of, as I said today, we are kind of doing this more abstract stuff, and next week we will work in more concrete formulas, which is actually pretty much sufficient for everything you want, but since I wanted to give some sort of rigorous introduction, then let's stick to this one. So, and here maybe I can mention one more thing that I used in preparing this, which is a very good resource, although it's a bit brief, but going in parts. There is this famous book called Quantum Fields and Strings for Mathematicians. And strings written by a compendium of authors. And the thing I'm explaining is essentially on 2 pages in there or something. So it's a bit brief, but some ideas are there. And maybe the name. Okay, so why is it called supermanifolds? So it's called like that because it is the kind of underlying or supergeometry. It's like the underlying picture. It's the picture underlying what is called supersymmetry in physics, where you have things which are even and things which are odd, and they kind of interact nicely together. You can have coordinates which anti-commute, and that's precisely the framework that we have here. So super in general, the dictionary is that super means that there is Z2 grading. There's even and odd stuff Okay, so now let's start with setting things up. Let me say that in a superalgebra, or more probably a, but I will put it in parentheses because I won't repeat that, it's super commutative associative unital or just superalgebra. Okay, I will assume all of that. I mean, proper name should probably contain all of that. I will just call it superalgebra. So this thing is an associative unital algebra structure on this algebra structure on a vector space A, which is on a vector space A, which decomposes into two bits, even and odd. Okay, so this is a direct sum of vector spaces. Okay, so I just take this as one vector space, and I want this to have an algebra structure, so which means that I have a multiplication and I have a unit. Okay, so associative unital algebra means that there is associative multiplication, associative times, and a unit 1. But now I want that it's all defined on this kind of space which splits into two bits, and I want that this operation, that the multiplication operation, the product, is compatible with this, which respects this Z2 grading. In other words, it means that if I take something that's even times something that's even, I want that the result is even. If I have something that's even and something that's odd, then I multiply them, then I want this to be odd. The other way around, odd times even is odd. Okay, odd, and two odd things are even, just like numbers. Okay, so I want that this multiplication respect this, and now I have to address the supercommutativity. So u times v, I want it to be -1 to the parities times v times u. Okay, so these objects here are, this is the parity of u. So even or odd. So integer mod z2, mod 2. And for all, okay, I mean, okay, in writing this, I kind of assuming that u and v have a fixed parity, so u and v are either in here or here. Okay, so for those of, okay, so more shortly, if you want, it's like a associative algebra, associative unital algebra, which respects the Z2 grading of the underlying system, and which is commutative in this kind of causal sense that we saw in one of the first lectures, maybe the first lecture, that it is commutative, except that you have to take into account the sign you get when you exchange these two guys, and that's precisely the sign of this type. Okay, so this is precisely that causal sign rule. Okay, now exercise for people. Simple one. What is the parity of 1? Does it have a fixed parity? And if it does, what is it? Is it even or is it odd?
It's even.
Why is it even?
Because if I use the supercommutativity, then I have 1 is -1 to
I see.
parity
Okay, yeah, that's yeah, that's right. Yeah, if there is anything odd, then if you take u to be 1 and v to be anything, then yeah, you should get this thing to the. I mean, what you said, yeah.
But could it be mixed? Does it prove it's not mixed?
I think so.
Probably yes.
I mean, what I had in mind was that.
Yeah.
I mean, if you multiply something even, then you know that it should be the same thing, so it should be even still. So it should send even to even, and it should send odd to odd, from which it should follow that it's even. So yeah, this thing is even. Okay, any questions for this part?
0.
Okay.
Yeah, what is the parity of 0?
So, well, 0 is both even and odd, right? Because it's
Yeah.
even and odd. Because it implies both a even and a odd. Okay, feel free to forget that you heard this. Okay, let me give you. Okay, I think it's good to make. Okay, let's make 10 minutes break and then I will continue with examples and with defining what supermanifold is. Okay, so with a brief update on the how to properly pronounce names, we continue. Right, so we define what a superalgebra is. Looks like an algebra, but it's super, so it has like Z2 grading and graded commutability. And so what are a bunch of examples? Well, zero algebra. More generally, an ordinary algebra. Maybe I shouldn't be writing this. Anyway, an ordinary algebra, A tilde, associative unitary. So this is a superalgebra concentrated in the even degree. Superalgebra, where the even part is this A tilde and odd part is 0. Okay, so normal stuff embeds into this super world by simply putting 0 to the odd part. Now, slightly more interestingly, if let's say V is a vector space, then we can form the exterior algebra of V, and we can take this to be A. Okay, it is an algebra, simply by wedging things, right? Well, yeah, it is unital, it is associative, it is graded commutative. Now, what is the even and this is a superalgebra? What is the even and what is the odd part? Okay, anyone guess?
So even will be the even degree
Yes, so this is the even.
for the vectors.
So this is, let's say, sum of this is the odd even for all odd powers. And then if you have an algebra and you have a super, for instance, something like this, you can tensor them and it's still an algebra, a super algebra. So, okay, let me just go directly to the a bit more, one level higher. So, superalgebras. Oh yeah, I didn't say what morphisms are, but I guess you can guess. So, let's put it here. A morphism, superalgebras. Is a parity preserving morphism of ordinary algebra. Is a parity preserving morphism, algebra morphism superalgebras are just ordinary algebras with some extra condition that preserves grading, and you want also morphisms to preserve this grading. So even is mapped to even, odd is mapped to odd. Okay, so now we have a well, if you wish, a category of superalgebras. We know what superalgebras are, and we know what maps within superalgebras are. Okay, so now we can take this to be as a target category for our sheaf. So we can now talk about sheafs of superalgebras. It simply means, you have a space, to each open subset you assign a superalgebra, and restrictions should be algebra maps, morphisms. Okay. And so what is the kind of the first interesting example of such a sheaf? So let's take the topological space, which is just R to some power, where P is a prime number. Okay, no, this is a joke. It's an integer. P is an integer. Okay, so no, sorry, not positive integer. Okay, so we take this to be a topological space, and on this now we have an interesting sheaf of superalgebras. So what is a sheaf? Sheaf is something that takes an open set and assigns to it an object, in this case a superalgebra. And this sheaf here, it's called, I don't know, let's not call it anyhow. So to each u, it assigns the following superalgebra. You take the smooth functions on that u. So here u was an open subset in Rp. And you take this thing times wedge of some vector space. Yeah, or even take that vector space to be R to Q for some Q. Okay, so the kind of input data for this is that fixed P and Q in non-negative integers. Non-negative. Okay, so I'm at each open subset of Rp, I'm taking a superalgebra, and that superalgebra is simply a product of these two guys. So I take smooth functions, tensor this exterior algebra. How do I multiply two such things? I multiply them, well, functions times something, I multiply by functions times something, I multiply functions, I multiply the somethings. Okay, so is it clear how this is an algebra? Okay, I take two functions. Yeah, okay, I said so. And well, the restriction map is obvious. I'm just restricting to, if I go to smaller subset, I just restrict this part, and this part I just leave intact. This is kind of an observer. It doesn't really do anything at the moment. It just makes the stuff more interesting and not really commutative, but rather super commutative. And let me call this example this symbol. Is this symbol called sharp? Okay, sharp. Okay, is it clear that this is kind of the important point to understand?
So if I took P equal to Q, is it the same as the differential forms on R and RP?
Well, depends on what you mean by this. Oh, okay, that's what you mean. Yeah. Yes, yes, it is.
So we don't care about like how they transform, I guess, additional.
Yeah, here no. Here I'm just saying that I have a sheet like this. Okay. Okay, and now comes the big definition. So a supermanifold and I try to be consistent, and I try to not use curly letters here, because now I will use curly letters, curly M, of some dimension. In this case, dimension would be a pair of numbers. Dimension PQ is a topological space. We'll make a remark in here about what kind of topological space. So far, let's take any. A topological space which will be denoted like this. Okay. Together with a sheaf of superalgebras, and I will call the sheaf O of M of superalgebras. Which is locally isomorphic to sharp. So I want to have something that locally looks like that. That's kind of the idea. Okay, so several comments.
Is this like the structure? Would you call it like structure sheet of the space?
Yeah, why not? Okay,
So
so
you don't need to call it. Just if other people call it like this.
yeah. So we call this thing functions. I want to call it functions, or you can call it a structure sheet of M. Okay. Now this curly M is the thing that will play the role. This is the thing that we will pretend that this is our new space. But what it really is that this M is really a pair. It corresponds to some ordinary topological space, really something that has points, and then a sheaf. Okay, so it's really a pair of data. Okay, a couple of remarks that I maybe will just say. Okay. So, well, one thing is that you can, okay. One remark is that you might want this to be, this topological space, you can assume it has some extra properties if you wish. So you can, if you like, depends on what you like, if you like, you can take this to be Hausdorff, assumptions. Depends on your case. Second remark is that is there everything clear in the definition?
So maybe I will ask about the local isomorphism.
Very good. Thank you. That's the thing I wanted someone to point out. Yes. So great. So there is so the word locally is relatively harmless here. It just means that I want that in this guy, which is really some sort of space, I want that at each point there is like an open neighborhood in which I have an isomorphism to star, to sharp.
Mm-hmm.
Now the slide. Okay, so the thing I did not say is what it means to be isomorphic, because I didn't tell you what maps of such objects are. But I decided to cheat here a little because in order to say what, I mean, isomorphisms are rather special classes of maps. They're kind of easier to say, you know. Here it just means kind of the obvious thing, the only thing that you can take. So that you have like two spaces, topological spaces, and you want to have a homeomorphism between them, and you want that if you identify them, then the sheaf is like there is not much. Fortunately, there is no like freedom in how to interpret this thing. So, how should I say this? So if you identify these things, then you should have a. Each time you have an open set here, and you map it here under this map, it maps to some other guy. I don't know, U prime, and you want that the corresponding sheaves that you have here, and here would be some F tilde or something. U prime, you want that they are the same, or that they are isomorphic and as algebras in your respective category, and restrictions is whatever, tough restrictions. So I'm deciding to not talk about that, but rest assured that it's just that. It really means that they kind of if if you identify the two spaces, they should coincide. The corresponding structures they are just the same. So I didn't tell you yet what the map of such spaces are, but I'm saying that the isomorphism is kind of a simpler way to state it. It just means that
But simply, if your topological space would be directly RP, it would be just the thing.
yeah, that would be an example for that, and that would be our first example. RP with that sheaf is a special type of. It's kind of like the local model of the supermanifold, and others are things that look local like it.
Okay.
Does that help? Or if not, then please ask me because this is the first time I'm trying to present this in a sort of rigorous way, and there is bits in which I.
So I have a question.
Yeah.
Because if you have, this looks kind of like special example like these local array spaces, and there I think the data of the sheaf map has to be kind of extra together with the map from x to y, because this kind of pullback of functions is not something that would come naturally. You know, if you have a map of just.
Well, yeah, I mean, this is two data. Like there is the identification, and then you need to identify.
Okay, so you have these two things.
Yes, but yeah, technically yes.
But it's not part of the definition. You don't need to specify. You just need to know it exists.
Yeah. Same as for like manifolds and identification with Rm. There just need to be some, and yeah, very good. Again, let's maybe reiterate that all that we are doing today is that we are kind of building a rigorous framework for this, but if you actually want to practically work with the stuff, then you need much less. It's just that today I hope to develop some kind of intuition and ideas about what's happening, and then we can work with things more freely and more kind of enjoyably maybe.
So somehow, does it follow from the definition that the body is a manifold?
Yeah, that's the next thing. Yes,
Okay.
thank you. So, yeah, this is. I was fighting with how to present this definition for quite a long time, and then I decided to do it in the way they do it in the book,
Yeah.
and they do it in this way, which kind of seemed the cleanest and the quickest way to do it. And okay, so. And then now let's do what Brian said. I think before that, let me maybe say the two things. So part of the definition. Okay, so we say that an open submanifold or supermanifold, but we don't write super all the time. Let's say U under M. By this we will just mean that it's an open subset. Again, there will be some open subset of the topological space, so this is really just a subspace, a topological subspace with the restricted sheaf. So we take this pole of M, which is defined over the body of M, and we restrict it over this U. Okay, the way you should read this definition is just, I'm just saying that the kind of, or part of the way to read this definition is that like all interesting topology will simply be happening in the kind of topological space. It's only there that you take it to be a subset, and the rest you just kind of induce. Okay, that's kind of the underlying, the undertone of this. Okay, now we'll do one more thing. So for M supermanifold, we define the following thing, which will be the sheaf of ideals. Is that meaningful way to say? Okay. Well, we'll call it I, and this thing will be simply take this guy, the odd part, and take the generator. Okay, so recall that it's O of M, so supermanifold consists of a space and some sheaf of superalgebras. Now in this sheaf of superalgebras, over every, the word sheaf, don't be confused about that, I'm just saying that over every open set in here, I can evaluate the sheaf and I get sections of the sheaf, so I get a superalgebra. Okay, so O of U U is a superalgebra, so where U is a subset of open subset here. So this is a superalgebra. Superalgebras, they always decompose into an odd and an even part. This is even, and there is an odd part. So what I'm saying is that take the odd part, and then it's an algebra, so you can just generate an ideal by this. So you just multiply these guys by everything, and you get some sort of subspace, which will, in general, will not be the whole thing. Okay, so this is what I mean. It's an ideal generated by the odd part. So, for instance, so one example. So in that sharp example here,
It never is the whole thing.
sorry.
It never is the whole thing.
Yeah, it never is the whole thing. Yeah. Okay. So so in this guy, what is the? So let's try to see what is this ideal in this guy. Okay. So does anyone see what is the odd part of this super algebra? First, not the ideal. What is the odd part? So what is the odd part of this? Sorry? No, it should be the. I mean, the exterior part also has even odd bits in it, depending on the priority, depending on whether you take even or odd.
It's the infinity times the sum over the odd powers.
Right.
Of this.
So it's like, yeah, so this is like wedge 1 of V plus wedge 3 of V plus wedge 5 of V plus etc. So it's that. Okay? And what is the ideal that this can generate? So if I take the ideal and write it like that. Write it all. Okay? What do I get when I take the ideal? So I take this thing and I multiply it by the whole of this thing again. What do I get?
The same thing again.
Same thing as this one? No, because I can multiply it with, if I multiply it with like wedge of V, with V, just element of V, then this thing will, like I have wedge 1 and I multiply it with something in V, I get wedge 2. Wedge 2 is not in here.
Yeah.
Yeah, for the international viewers. So you get this thing, but you get wedge 1, wedge 2, wedge 3, etc. You get all of them apart from wedge 0. Okay, that's already comes from the fact that this thing generates, this thing multiplied by this generates everything in here. Okay, so more shortly, this is. Let me write it like this. Okay. So now proposition, which we essentially proved now. So if M is a supermanifold, I will just shorten the super MFLD. Then if I take this ideal and I quotient-by it, what do I get in this local picture, in this kind of sharp thing? What do I have? What do I get if I take the whole algebra again and I mod out by this ideal? Right? What if I remove this thing? What is left? C infinity, exactly, times wedge 0. Okay, so then this thing is a sheaf of ordinary commutative associative unital algebras, and it will locally be isomorphic to the thing you said, so to C infinity of m. So if I want to say it again as a sheaf, so I should say that it's locally isomorphic to this model where you have R to the P. Okay, like our supermanifold was locally, where is it? Locally it was this sharp, so it was R to the P. But now not with this complicated algebra, but just with C infinity. Okay. I'm not writing C infinity of something because I want it to be like a sheaf, so I don't feed the set in it. But it's just the thing that you observed before. So if you take this and model by this, then what is left is C infinity of n. Actually, sorry, what was that n is u? Doesn't matter.
Was it only locally isomorphic?
Yes. Yeah, because I mean, what we did here was this thing was for a special case of this.
Sorry, because you wrote also RT, but as a sheaf, this is just C infinity over m over the body, or not? That quotient, right? Forget about what like the quotient O m by I. Isn't it as a sheaf C infinity over the body?
Yes. Well, no. I mean, morally, but I mean the body here is not the manifold yet. We haven't talked about it. So far it was just a topological space for us, and it is in this way that it becomes a manifold.
Okay. I see.
But yeah, good point. Very good point. So yeah, so hence this thing which I guess we can call it the body. Let me add that in definition. So this thing is called the body, or sometimes the base, I think, of the supermanifold. Okay, so now we started with a supermanifold, and we know that if you take a quotient, then you get some simpler sheaf. It's over the same body, but it's now isomorphic locally to this model. Sorry, it's over the body of supermanifold, but it's locally isomorphic to this thing. And if you think about it, then that's kind of morally what the manifold is. It's like something that locally looks like this flat model. So in fact, this thing should show you that this thing together with this quotient is a smooth manifold. And following the book that I mentioned, I will call this the reduced, like either reduced or red, whichever you prefer. Maybe I should use different color. Okay, so the way I presented it here is that supermanifold is a topological space with a bunch of extra structure, but in particular that extra structure gives you a sheaf that you can use to build a smooth manifold out of this. And in fact, what you should think, and that was the way I suggested before, is kind of like the moral of the story is that the smooth manifold is, sorry, the supermanifold is really something like you start with an ordinary manifold, this guy, and then you put some extra coordinates on it which are kind of odd in both senses of the word. But to make it formal, you need to say it like this, or in some equivalent way.
But you are never changing like the topological space. So that's same for both. So you are only changing the sheaf kind of. If you
Yes,
go from
that's right.
super to the reduced.
Yeah, so they have the same underlying topological space. So maybe while I'm erasing, well, do you ask me questions? I can say that like this thing appears in like various contexts. In physics, typically associated with supersymmetry, so you can formulate string theory. I mean, the supersymmetric version of string theory in terms of super Riemann surfaces, which is like a super manifold analog of Riemann surfaces. You can study the moduli spaces. That's a big and complicated thing. You can also study the alternative approach to string theory. You can study supergravity again using describing your fermionic field as sections of some bundles which are really odd. So they are like some fermionic, some odd sections of some odd vector bundle. But there is also many other non-physically relevant things in which this appears, and we will see them very shortly. Yeah, any questions in the meantime? I'll take a sip from the water.
Will you talk about the map which you get from the body to the big manifold?
I will now.
Is it
I will first define what the map is. Yes, sorry.
no, that's fine.
Okay, so now we have the objects that we are interested in. Now what about morphisms between them? So what is a map of supermanifolds? This should hopefully answer both questions from Jan about the maps of sheaves and the thing we're asking now. So map of supermanifolds or morphism of supermanifolds. M to N, let's say. Let's go F. So again, it will have some sort of real topological data, but it will have some sheafy things. So this is given by the following things. Data. So first of all, we have continuous maps of topological spaces, and this in accordance with the previous notation will be called F in absolute value. So this is the map that goes from the underlying body to the other underlying body. Okay, so there is really something that can do something with topology. And the second part is that you have to say some sheafy information, and that sheafy information is the following. So for all open subsets of N, so take this, open. We want to have a morphism of superalgebras. Morphism of superalgebras. Okay. So, because you should think of this sheaf as morally some sort of functions, and functions usually go in the opposite direction. So you can kind of pull back functions. So I have to describe a map that goes in the opposite direction. So I will draw a picture in a second, but
Could you just go back a little bit to repeat the argument how you obtain from just the topological space the condition that it has to be a manifold?
So it's not a conditional, but it's more data. So you have like this thing has a sheaf of something. So the underlying idea is that many things you can formulate in terms of sheaves.
Okay.
For instance, you can define a smooth manifold in terms of sheaves. You can say that it's a topological space with a sheaf of commutative algebras. functions on it. And you want the condition that locally it looks like this. So that's kind of an alternative definition of manifold. I haven't proved that it's the same as the usual one, but I'm kind of claiming that that's underlying this thing. So you have this thing with a sheaf of superalgebras, and once you take a quotient, you get another sheaf, which is now a sheaf of ordinary commutative algebras, which locally looks like this. Hence, it's a manifold. So that's the underlying thing is that alternative way to describe a manifold is to say that it's topological space with a sheaf that looks like this locally.
So the point is that this sheaf is already basically a part of that sheaf that's already present there, so that this is to give you also the manifold.
Yes. So the sheaf of superalgebras has more information, but in particular, if you model by this odd nonsense, then you get like something that looks like ordinary functions and a smooth manifold, and that defines you a smooth manifold structure. Thanks. Right. So here there should be f inverse of v. Okay. So I want to pull back. If I have an open set here, I take a preimage. It's an open set here. That's what it means to be a continuous map. And I want to have a map. If this sheaf was functions, then I want to pull back functions on that open set and get functions here. So I'm just writing that in terms of sheaves. So you want to have a morphism, and of course there needs to be some condition, and the condition in here is just the it's compatible with the rest of the things. Which means that if I have v prime inside v, open, and this one is also open, then I can do that. I can sections over this open subset v into this guy. Okay, but I can also do the same for smaller stuff. V prime. But because these things are sheaves, then if I go from bigger subset to a smaller one, then I get a restriction map which goes this direction. And the same I get here, because again, the preimage of v is contained. Preimage of v prime is contained in preimage of v. So I have a kind of sheaf restrictions here, and I wanted this commutes. It's the obvious thing for requirement. There is nothing like nothing to say about this. It's just it behaves nicely, is what it says. And in terms of notation, so this map. So here, so the image. Take v in here, v in O and v is called f pullback of v. Okay. So this I'm introducing notation that really matches what you normally expect. So this is like a map, and this is a pullback functions.
So we don't have any more. Because I think we have an extra condition on the pullback coming from the clearing spaces thing. That's not a lot of strokes it needs to map. It's the maximum ideal.
My understanding is that here it follows somehow automatically.
Okay.
Yeah, that's what they say in the book at least. I wanted to make a comment about that in a second, but not prove it. But okay, I now in slight doubt, but I think it don't.
It sends the odd part to the odd part.
Yeah, but the odd part is not the maximal idea.
But doesn't it follow from this?
Does it follow for like smooth manifolds? Just
I think so. I think so. That's a very good point. I was hoping that we can discuss this later. I hope I'm correct on this, but I think it should follow. But I will write at least what I mean. But so one note, well, but this note is actually is saying that like an ordinary manifold is just correct. They should correspond to normal maps. An ordinary manifolds. This would be. This should give just the usual definition of maps. Okay, where this thing would be map of manifolds, and this thing would be well, anyway, it should reduce down. Let's not go into details. But what I wanted to kind of at this point say some sort of nice example of a map is that we have this quotient and if you remember that this thing was the sheaf, so for a supermanifold M, so we have this quotient, and remember that this was the structure sheaf or function on the supermanifold, and this was the function on the radius manifold. And so this thing, in fact, defines a map. Let's call it, I don't know, I, from this M right into M. And moreover, as a detail, some kind of the underlying map of topological spaces is the identity. Okay, so what I'm saying here is that if you have a supermanifold, then it's a supermanifold, but this thing gave rise to an ordinary manifold, which was called like this. And if you remember the construction, it's here. So the construction, as was said before, they both have the same body. Like the underlying topological space here is the body of the supermanifold. So they are kind of sheaves over the same manifold, the same topological space. And I'm saying that if you take now this quotient map, which is kind of part 2 in this data, and you take identity on that underlying space, which would be the part 1 of that data, the together that precisely fits into the definition and gives you a map of these supermanifolds. Or even more quickly, you know, like in order to have a map like this, you need to have a map from functions here to functions here. That's this map. Yes?
Can I emphasize that there is no canonical map in the other direction?
Yeah, there is no canonical map in the other direction.
So you should not imagine these as bundles.
Yes, you should not.
But you can non-canonical.
Yeah, there are no canonical maps.
Yes, I will mention that in a second if we have time. Yeah, we will. Okay, so things to remember: there is always a map from the underlying smooth manifold to the supermanifold, but there is no canonical way the other direction for supermanifold.
But sometimes it can be useful thing.
Sometimes.
Is vector maps.
But yeah, so yeah, I will comment on that. We will not consider that in a second.
So, do you call this an injective map? I mean,
Yes,
does it make
yes.
sense?
I would call it an injective map. Yes, that's right.
So, because in it's contravariant on the sheaves, right? So the sheaf maps are what surjective. So on the algebras, the maps are surjective, but on the topological space, it's what is an atom. So you call this injective on the supermanifold.
I definitely yes. Okay. Yeah. It should be injective in all senses of the word injective if one gives it an appropriate definition.
Okay.
Also on the level of coordinates, I mean, so far this is pretty abstract, but when we will see this in coordinates, it will be kind of clearer, and then it's really just like you set some coordinates to 0. Or the other way. Yeah, you set some coordinates to 0. Yeah, so where we, that's another way to see this. Yeah. So if you prefer coordinate description, to which we will get soon, this thing is just saying that if setting odd coordinates to 0 is a consistent way, is a consistent thing to do, and it defines you this map. Say that. Okay, so now we are reaching the pinnacle of abstraction. So from now on, maybe after the next remark, it will go down to a little bit more concrete structures, and you will see why these abstract definitions are actually meaningful. So there will be a proposition which actually links this to kind of coordinate picture. And that is kind of the underlying reason why this is a meaningful subject. So as was mentioned by some people from now, so some people notice that this is what is called a in more generally this is called a ringed space, or a locally ringed space. So let me make one final kind of abstract thing before going back to Earth. So we call it remark with a start, because this is for people who know what locally ringed spaces are. If not, then feel free to ignore this. So a supermanifold, in fact, is the type of a more general structure, is a locally ringed space. Which means that OM, this sheaf, is not any sheaf, but it's a sheaf of rings. Okay, it was a sheaf of algebras for us, so that's rings in particular. With one extra property, that the stalks, again, if you don't know what stalks are, then don't worry. Stalks, which are called this, where this M is in the body. Stalks are local rings. And what does it mean to be a local ring? That means that they have a unique maximal ideal. And what is this ideal in the case at hand? So we saw that you have this map that goes from OM to this quotient. And on the level of stalks, if you know what stalks are, this gives a map of stalks, and the map of stalks goes essentially to this kind of you have this. There was this reduced thing, which was actually a smooth manifold. It had a sheaf of smooth functions, and this in you see the map of stalks. And here you have the map, which is the evaluation at that point M, which is a map of, which it's a well-defined map of rings. And you take the kernel of that. That's the maximal ideal. I'm claiming that, I'm not proving that. I'm just saying that if you really unpack what this means, that this is a maximal ideal of the stalks, and the claim that I mentioned to Ruda, that I hope the belief is correct, but I haven't checked it myself, and but I think I saw this how this goes. So, and the map of supermanifold, as we defined it, should be automatically a map of locally linked spaces. The map of automatically a map. So it should fit into that framework of locally linked spaces, if you know what it is. If you don't worry, you'll never mention that again. Okay. So now let's go a little bit downward and let's discuss examples, because this is okay. So first of all, as was mentioned by Frederick, so we had the thing from before, that this kind of hashtag or chart thing. So remember, this was a this was a pair of a topological space with a sheaf of superalgebras, and that sheaf was just smooth functions on the given open set, tensored with this exterior algebra over R cube. And I will call this deserves its own name, and this thing is called RP/Q. It's like the analog of the Euclidean space, or like analog of this kind of RNs. And you saw that in the definition of supermanifold, the supermanifolds are things that are local like this. Okay, so this is kind of a basic example. Now, okay, let's discuss that example a little bit more. So, okay, so maybe to match it with the previous notation. So what we are saying that the structure sheaf of this example is this, and if I evaluate it on the whole space, then it's that thing evaluated on RP. Okay, sheafs are something that needs to eat an open subset and then produces the corresponding set of sections. Okay, so this is what you can call global functions, global sections, global functions. But okay, but now let's so maybe okay. Let's now call the standard coordinates on RP. Let's call them x1 up to xp, and call the basis, the canonical basis of the other guy, RQ. Let's call it psi1 up to psi q. And then this thing means, if you look at it, so it tells you that in particular, inside I can see both these and these guys as particular elements of this guy. Okay? So each of the xi's and each of the psi alpha I can see as being a particular elements in here. Okay? Because coordinates on RP, there are special types of functions on RP. Okay? So they live in this part. Technically, when I say xi, you really want to be rigorous at this stage, you should say that this means I take xi tensor 1. Okay? I take here 1. But I won't write that, I'll just take xi. Similarly, if you take the basis of RQ, then you know that these guys are generated by having the basis and wedging things together. So, well, so in particular, these xi's, they live in degree 1 part of here. If you want, you can call this 1 tensor psi alpha. But it's fine to just say psi alpha. Okay, so the moral of the story is that if I pick this, if I choose this data, then it produces a bunch of special elements in here. And in some sense, you can see this algebra is being generated by those things. Of course, this is not polynomial, this is all smooth functions, so it's not really. But morally, you can think of these things as like being generated from this algebra. So I will call these guys, these are called coordinates on this RPQ. Okay, because they generate in quotation marks the ring of functions. Okay, takeaway message, which will be the only thing that we'll remember next time, or we will need maybe next time and a half, is that there is this special supermanifold that looks like this and is described locally by two sets of coordinates, these guys and these guys. And if you look at their parity, then these things are even and these things are odd. Okay, just examine the parity here, the degrees where they live. Okay, is the example clear to some extent? Good. This was example 1. Example 2, which I prepared before I prepared example 1, which means that it's a little bit of a, well, not really useful, but anyway. So if V is a vector space, I mean it will be a special case of that. If V is a vector space, then we can define a supermanifold, which is called pi V. Okay, this is capital Pi, in case there is someone who likes typography. This stands for parity shift, and that's why it's P. I hope. Parity transform or parity
Function.
okay, flip no, but
Parity change. Reversal.
parity reversal is even better. Yeah. Okay, good. Thank you for the suggestions. Okay, so I define a new supermanifold. So how do I define a supermanifold? I need to specify a pair of data. I need to specify the topological spaces. In this case, the topological space is a point. So I think I denote a point like this, but okay, just to avoid all confusion, let me put it in set notation. So a point. But the sheaf over that point is not trivial. Now what is a sheaf over a point? What data does a sheaf of a point correspond? So sheaf is something that eats an open subset and it produces something. Now how many open subsets there are on a point? 2, exactly. Someone has more? No? Okay. So it's the empty set and the point itself. The empty set, we know that every sheaf associates just a singleton to it, so that's not really important. But so to kind of tell you the data, I just need to tell you what it assigns to the whole space. And what it assigns to the whole space is this exterior algebra on the dual. Okay, and what is happening here? So let's say if E alpha is a basis B, then if I take this wedge V star, then any element in here I can see it as a I don't know, alpha. This is like alpha, smaller alpha because it's hard. Okay, whatever. IJ. No, I called it alpha. Should have stick to my preferred notation. So any element in here, I call it F. You can write as 1 over P factorial F alpha beta, and then you have E alpha wedge E beta. And that's, you pick a frame, a basis, then and there's a P of them. This is a general element, and you see that if you want to regard this as your function, then you see that as an algebra is generated by these E alphas. So the E alphas are the coordinates here. So E alphas are coordinates. So sorry?
They were excited.
They were excited before, yes. their coordinates on pi v. Okay, so which means that they are generators of the sheaf of functions there. And so what was, morally what is happening here is that your vector space, each vector space in particular is a manifold. It's a very boring type of manifold, but it is a manifold nevertheless. And if you pick a basis, then basis gives you a set of coordinates. You have linear, if you take the corresponding dual basis, which is this presented these guys, in your original vector space that defines a bunch of functions there, so it's a bunch of linear coordinates. So you have an ordinary manifold, and that ordinary manifold has a bunch of coordinates. And what you are doing here with this parity shift is that you are instead taking a manifold which has the same coordinates, I mean at least they are look the same, but they are now odd, right? Because they live in this wedge 1 V star, so they are odd. And that's why the anti-commute that corresponds to the wedge in here. That's why I call the parity shifts. And to make it meaningful, you the underlying topological space that you have is no longer, well, some n-dimensional space, but it's a point, and instead you are kind of moving the coordinates here in this sheaf of functions. Okay, so maybe picture, or not really picture, but this guy with these things was an ordinary manifold, and these are even. And what parity shift does to you is that you take the same stuff, but you proclaim that these things are now odd, and this is now a supermanifold. Make sense?
So for you, the capital pi doesn't change like the parity of vector space, but produces the supermanifold when the superdirections are those. So
yes, that's the way I presented it. Yeah, I see what you mean.
because we could have also similar
Yeah.
kind of functor which takes vector space and produces the corresponding manifold, with smooth functions on the vector space.
Yes. Now here mainly there's a. I kind of tried avoiding talking about vector spaces and their shifts and stuff. I just wanted to do directly. So I wanted to minimize the confusion or maximize the confusion.
Yeah, I think it's good.
And okay, so we should end, but let me maybe give the final example. Is this example clear? Is it? Yeah, as Brani was saying, this thing actually tells you that this parity shifted V space, if you pick a basis, that it really looks like this, which is the special case of the thing above if P was 0. And this is a special case of this, where the even stuff is 0 and the odd stuff is precisely as many generators as the dimension of V. Okay. Now, the last example is that if E over M is a vector space bundle, then we can define a supermanifold, which is called parity shifted E. And this is a supermanifold whose base will be, or whose body or base will simply be the underlying thing here. I'm doing now what I did in the previous example, except I'm doing it point-wise. At every point I shift the fiber to the odd direction. And if you think about what it means this, that the sheaf will now look like this. You take a vector bundle, you take the dual of it, and then you take the exterior powers on that. And you look at sections. So, and again, in terms of coordinates, what does it mean? So if you pick a frame, a local frame, over some neighborhood of E, and if xi tells you, on one side it tells you that xi together with the dual things are coordinates on your E, right? That's what it would mean in ordinary geometry. Coordinates on E as a manifold on the total space. Okay. And on this shifted thing, it means that here xi I will have xi E alpha are also coordinates on this supermanifold. But now, while these guys remain even, these things will be odd. That's what we did. We kept this manifold to be normal manifold, but we moved the fiber directions into this odd direction. So we essentially proclaimed that these fiber coordinates are now odd. So here they are even and even. Okay. Or maybe more in line with the previous example, if you look at that thing, and you look at the general element here, sigma, and that sigma will look like sigma alpha beta depending on x times E alpha wedge E beta. Okay, so any section of this wedge power can be seen as some bunch of coefficient functions times the dual frame wedge with itself. And here you can see that a general such thing I get if I get a bunch of E alphas, put them together, and a bunch of x's, morally speaking, maybe completing. That's why these things are coordinates, because they can generate all such things. Okay. There is a little bit of space, so let me just state the theorem, because I'm not going to prove it anyway. And this is the so-called bachelor theorem. It says that every supermanifold is isomorphic to phi E or some ordinary to bundle E. It turns out that this example above, this kind of X hosts in some way all the supermanifolds, at least in this smooth category we are working in. But you should not take, you should be careful with this, because this is in fact non-canonically isomorphic. So as categories, vector bundles and supermanifolds are very different. I will take that again next time, but just to say that in some sense, if you pick a supermanifold, then you can kind of make some local choices, and you can always identify it with a thing of this type, with pi with some vector bundle. But it is a very non-canonical thing. If you choose different data, then you end up with a different thing at the end. So you should not confuse the two things as being like the same in some sense. Also, the map between them are different. The maps of vector bundles, they have to be linear in fiber coordinates. These things totally don't have to be linear in these old coordinates. Which we will see that next time when I discuss how maps look in like next time we'll discuss the proposition which tells us how this actually connects to coordinates. To using coordinates, and then it's really like one-to-one, and in fact it shows that you can really think and work with these things in like a natural way, like you would do in everyday life, like in coordinates. So yeah, that's for next time. Any questions?
So can you go back from a supermanifold and define two non-isomorphic vector bundles by picking local data?
Yeah.
So that's the claim, right?
Yes.
So this correspondence is like, subjective.
I guess the bundles are always isomorphic.
Are they? I don't think so.
I mean, if you just count dimensions, you have
Oh, I
number
see.
of
Maybe
points.
you're right. Yes.
No, in dimension yes, but like they can have different topology.
Topology, yeah, topology.
Really?
No?
But you
Right.
you reduce manifold to the
Which one?
you reduce manifold to all where it's the same topology.
The reduced one, yes, no, but like the vector bundles, like the vector bundles can be different, right? Like in principle, right? You can build isomorphism with two different vectors. Sorry, you can have two different vector bundles. I'm not sure. I never worked with it actually, but
Isn't the bundle always trivial?
oh no, I know I shouldn't be.
Because you can have a trivial and non-trivial case, it will be maps of supermanifolds, but you will not.
Okay.
You can make it commutative because you don't have enough morphisms in this particular.
I mean, take any non-trivial vector bundle and parity shift